Hi all, this is Mr. Yeager with Physics. We are introducing the unit on electricity, and when we do that, we start off with the concept of electrostatics. So in this particular video, we're going to be talking about electric charge, static electricity, and electric force. All right, we are looking at basically the idea of where does the electricity come from and the idea of storing this electricity. That's what we're looking at in terms of electrostatics before we move into circuit electricity, which basically obviously means it's moving around. It's moving around the wires. Okay? So here we go. So first off, quite a few terms to make sure we understand. Okay? The term electrostatics is it's electricity at rest. As the name implies, static. All right, static means still. It is electricity that's being held. There's all sorts of different ways of looking at this. It's the accumulation of charge. It's electricity being held. It's charge at rest. It's basically saying that the charge is being held on one object. That is our focus for today. But that's different from what we would normally just call electricity, because that would be the actual flow of these electric currents, of these electrons, as you probably have learned in prior science classes. Electricity is the flow of electrons through wires and objects, devices. All right? We have electric charge. That would be a big one for today. It's obviously that property of matter that creates a force. All right? We're going to get into some detail with this. That's kind of a vague definition. You've heard of charge before from chemistry, positive and negative charges, all right? But that is what's going to, when an object has a charge, then it has an ability to create a force, all right? So that's basically what we're looking at here. A charge is created by an imbalance of electrons and protons. So a little bit of chemistry, very, very little, all right? And then the last one is electric force. It's just another type of force that is out there. In this case, it's a force created by the attraction and repulsion of two objects that have charge. Okay, that is the key thing there. There has to be some sort of charge involved with that. All right. So we first want to identify what do we mean by electric charge. Okay, electric charge. Electric charge is what creates that spark or shock. Okay, so if you've ever had that static electric shock, that's because somebody has an imbalance of these protons and neutrons and has a charge on them. We know the two states of charge, positive and negative, all right? I don't think you're going to get too many questions on this part. Obviously, if we lose electrons, we become positive. If we gain electrons, we become negative. Obviously, that's something that everybody gets confused initially, but hopefully that's something that's self-understood just from being in chemistry already, okay? So it will become charged if it takes on a positive or negative, or gains or loses these electrons. All right? And this is something, what we're going to look at is how do we create this? How do we create this imbalance of electrons and protons? All right? One of the examples, obviously, is in the laundry. This is why all your clothes will stick together if you usually don't throw those fabric softeners or basically static fabric that basically will pull all the charge to it so it doesn't go on your clothes, all right? But a lot of times if you pull clothes out of the laundry, you'll hear that snap, 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 snap of the charges being released into the air, again, that excessive charge. All right, so there you go. So again, where does the electric charge come from? What does it do? Well, again, this goes back to chemistry. We know opposites will attract. Positive will attract negative, while like charges repel. All right? So, that could be a pretty standard question or something that could be involved with any particular type of question. So, we'll see that when we get to electric force, it can be attractive or repulsive, all right, depending on whether you have like or opposite charges. All right? Just some pictures there. So the charge is, again, what will create the force between the objects. If there is no charge, there will be no force. Most matter is neutral. If I put two chairs together in this room, it's not like they're going to start colliding together or trying to attract each other or repel each other. They're not charged at all. Okay? So a neutral object is not attracted or repelled by a charged object. Okay, so to create this force, you must have two objects with charge. All right. Again, some just simple pictures here. What we're trying to show when we have two opposite charges. On the left side here, we got negative and positive. They attract, but if they are like charges, they repel. So, where does this charge come from? Well, one thing we want to just mainly understand here. This is, again, I'm not sitting here going, oh no, now you're going to have to write chemical compounds out. No, 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 no. Okay? What we're saying is charges will never be created alone. Just like a force is never created alone, all right, a charge is never created alone. There must be a pairing of charges. So that's why I have the sodium and chlorine right here. The sodium is positive because it gave one of its electrons away to chlorine. When chlorine gained one electron, it became negative, while the sodium must become positive. We basically are saying there is a law that charge must be conserved. We must know where that charge goes. If something becomes higher and higher and higher charge, that means positively something else must be becoming higher and higher charge negatively. All right? It'll always have to be something where they basically, we have to account for all charges, just like we have to account that matter is conserved. That's all we're trying to understand here. All right? Charge must be conserved. All right? Now again, why does an object have charge? This one I'm just going to kind of quickly go through. Again, we know protons are positively charged in the nucleus, while electrons are negatively charged and moving outside the nucleus of the atom, and neutrons provide no charge. The electrons are obviously the things that will move. All right, we already know they're the ones that are on the outside of the atom, and they can move and move from one atom to the next. So that's why we can create a current with them later on. That's also why we will collect electrons, not protons and neutrons. They're too far inside the atom. We never really come into contact with the protons and neutrons. They're really far inside of that atom. These electrons spread out way, way, way from the nucleus, and therefore, even when I'm stepping on an object and I push down, I never actually get that close to the nucleus of the atom itself. Okay, so nothing too much there. Just obviously, where does charge come from? An imbalance of protons and electrons, and with the electrons being the things we're switching. So this is kind of one of the main points of electrostatics, is how do we create charge? And so there's three ways to create charge. There is friction, conduction, and induction. Okay? Obviously the last two sound very much alike. Let me go ahead and explain friction already. I don't even have any separate slides for friction because hopefully it's pretty straightforward. Friction, basically what's going to happen is we have to have some sort of touch and rubbing motion between the objects. The objects must be moving across each other. Okay? That's going to be different from conduction, where simply I touch the objects. No rubbing. I simply touch the object, and usually something is already charged there. Friction, basically what we're saying is you have that wall and you have that balloon. Okay? If I rub that balloon against the wall, what will happen is those electrons on one of the objects, whether it's the wall or the balloon, will get rubbed against the other object and move from one object to another. Okay, what I'm trying to show here is I'm basically saying the electrons are going to leave the balloon and go to the wall. All right? You never have to worry about which way they'll go. They'll basically always tell you that in the problem. But what they'll then ask is, all right, if I rub these two things together and the electrons move from the balloon to the wall and then I pull them apart, what charge does the balloon now have? Well, it lost electrons, so it should become positively charged, while the wall should become negatively charged. So friction will always create opposite charged objects. All right? It'll always create the opposite charge on either object. So you're going to get questions where it says you rub your shoe against the ground. The ground becomes positive. What does that mean? What charge does your shoe have? Negative. All right? That's basically all you're looking at here. And again, it's the electrons moving from one object to another. All right? The other two, I would again try to use some word association with it. Conduction will be touching. Okay, the objects touch, don't rub. Okay, they just touch. Induction, we will learn, is where we charge the objects with no touching. The objects stay away from each other, but you get them close enough where you will cause a change in charge between those two objects, okay, or adjustment of charge between those two objects. So, friction will form opposite charges when you rub them together. Conduction occurs when, and this is kind of already telling you a whole process of it, okay? The key words here is conduction will occur where you already have, so you already, that's one of the words we should have there, have a charged object. And it will tell you, I have a negatively charged object. I'm holding it. How did it become charged? Who cares? We don't know. Probably friction, who knows? All right, that's not important. All right? We have a charged object, which you then touch to a neutral object. Now, it doesn't have to necessarily be neutral. We'll talk about that briefly, okay? But we'll start off with what happens if you touch it to a neutral object, okay? There won't be any attraction. When you get close, it's not like that's going to pull toward it, all right? Because, again, we don't create this force between them until they are officially charged. But you have the object, you touch it right against something, all right? What will happen is, as it says, these electrons will spread to both objects. Both objects will become negatively charged. So that means conduction creates the same charge on both objects. The same charge on both objects. All right? That's when you're going from something that is already charged to something that is neutral. All right? So if this was positively charged, the other object would become positively charged as well. This is again called charging by conduction. All right? And so, let's see if this will show me in my little video again. Sorry. There we go. All right? So again, if we watch this little video here as it goes, we're going to go back to the beginning here. Go, go, go. Okay, we have a neutral object. This is called an electroscope. This is a negative charge rod. It touches, sends those electrons on down. This is an old device called electroscope where you have these two metal leaves at the bottom. When it becomes charged, we should see them separate because it repels. Then you bring in your hand. Well, guess what? You're going to get shocked because it's an imbalance of charge, and those electrons will leave to your hand. So this is charging by conduction. This can be positive. And then the electroscope will become positive. Same thing. When it's positive, that means the electrons are moving the opposite direction toward the positively charged object. All right. The big thing here is charge will balance out. All right. Charge has to balance out. If you have two objects that are different negative charges, they will go from a higher charge to a lower charge. I'll write that down. We always go from a higher charge to a lower charge. And what will happen is they will balance out. So for example, if I say something is 2 negative and something, this is kind of very general, and something that is 1 negative, if I touch those objects, if I touch those two objects, what happens is it becomes equally charged. Basically both objects will become, 1.5, 1.5. They will balance each other out. They will balance each other out. Okay? So that's what we're looking at there. All right, sorry about that. That was a little interruption there. But anyway, so what I was trying to show at the very end here, let me erase this one more time, just to show it one more time. Charge will always try to balance it out. So again, if we have two separate charges, one that is, let's change this up, like maybe -5 and one that is -1, if they touch, we will see a movement of charge from the higher object to the lower object, all right? Because basically we're saying the -1 is less negative or slightly more positive, okay? So some of those electrons will travel from one to the other, and what will happen is if I leave them together and then pull them apart, they should both leave at -3 charge. They will both balance each other out. Once again, this is showing you conservation of charge because total charge up top is -6, total charge at the end is -6. We're trying to balance those out. Basically, they get averaged out in a way. All right? So I think there's another, oh, no, going straight to induction. I thought I had something with another thing with conduction. So for induction, what we're looking at is, again, this is going to create charge without direct contact. So again, the pictures do a good job trying to illustrate what's happening here. We have this neutral object, this neutral sphere, okay? We can count out positives and negatives and see that they're equal. What happens is then I hold up a charged object. Something already has to be charged. Again, how did it get charged? I don't care at this point, okay? So we hold up something that is charged, but I don't touch it, because if I touch it, boom, those electrons will go to the other side. They'll start balancing each other out. What can happen, though, is if I hold it close enough, you actually will see the sphere start getting attracted to it, which that only means there must be a opposite charge on the other object. But what's actually happening is, in this case, when I hold this negative object up, it makes all the electrons move to the other side of the object because they're getting repelled. That'll create an imbalance of charge on the object itself. This gets a bit more technical now. Technically, we can then remove those electrons, and this sphere then becomes positively charged because we pushed all those electrons to the other side. If there's something that can then grab them and pull them off, we can create this positively charged object. So the thing is, don't worry about this ground wire. That is actually something that never really comes up on any test, on any of my things. All right. What I would try to have you remember more than anything is induction will create the opposite charge on the other object. All right. So if you hold something up that's positively charged, the other one will be negative. All right. That's what we're looking at here. All right. And that's how the questions would be asked. It's going to create an opposite charged object. All right. So that's what we're looking for. The thing is, if I touch it, it'll then take on the same charge, and then the ball should actually repel because then they'll have the same charge. Okay? So that's something that's often done in classes where you can see, you hold up this rod, you see this little object start being attracted toward it. Eventually they connect, they touch, the electrons travel over, and then all of a sudden you'll see the ball go, oh, sorry, let me draw that. There's my sign for that. It'll be pushed away when they become the same charge. Okay? That's because conduction occurs there. So I'm trying to show you induction and conduction. All right. So here's another example. All right. You have the two spheres here. You hold up a charged object. It becomes positive on this side, sends all the electrons to the other side, and then you separate them. Well, those two things will become oppositely charged. Well, guess what? If you put these two things close to each other, what are they going to do? They're going to attract. They're opposite charges. Okay? And in the bottom one here, that's actually what I was just trying to explain. Hold up an object, it'll attract, then it will touch. Once it touches, it'll become negative, and then it will repel. So again, make sure, that's a big thing. Make sure we understand when it should attract and when it should repel. That's a pretty straightforward question. Here's yet another example of conduction. All right, this one would be conduction, but this is showing you from a positive charge standpoint. This one is conduction. And what we're seeing here is the electrons are actually flowing up into the rod to make it less charged. And that's what it's showing. When you do touch, some of that charge gets transferred. Okay? But the overall charge should remain the same between the two objects in the system, as we say. All right. Just some quick other definitions. Insulators. These will be objects that the charge does not move through it very easily, which means it's not collected well, but at the same time, if it does collect it, it's not going to release it very quickly. Okay, so these are, again, we know what insulators are. They obviously don't move electricity very well. That means they don't move charge very well. Okay, I mean, that's what basically the rest of this is all saying. What we're going to be looking for more than anything is insulators or things that aren't metal. I mean, that's going to be our general concept for this course, is there things that aren't metal. Conductors. Conductors are objects that obviously do move the electrons through very well, okay? And then we're going to basically say metals. I know metals have different conductivities. There's some metals that are very good. There are some metals that are very bad. They're basically our insulators. But we're gonna essentially say metals are conductors, and they move electrons well, okay? So they're not going to hold a charge very well. Conductors will not hold that charge. They're going to release it very quickly. Insulators will hold charges actually pretty well. All right. So this leads us to electric force. All right. And in my classroom, when we introduce this, we usually use what's called a Van de Graaff orb. These are those little orbs that basically somebody touches, and you know, somebody with long hair, their hair will stand up. That's hair. That's one of my wonderful drawings. Okay, their hair will stand up. So because they're getting charged, and the idea there is, if you're holding that, you become charged. So every hair particle you have, every strand of hair you have, will become the same charge. It'll all take on the same charge, which then that means it tries to repel itself from each other. That's why your hair spreads out. So the thing is, this leads me to electric force, because while I'm usually using this, I'm getting shocked a lot, okay? And that's because there's an imbalance of charge. And what happens here is that electric force is being produced by that object. That shock is created by a force. It's a force that's moving those electrons from one object to the other, and we can feel that as a push or a pull. And so again, you might have heard, hopefully nobody get really injured, but I'm sure people have heard of people being blown back by electricity, or being held by electricity, where it's like, why won't that person let it go? They can't. They're actually basically have a force acting on them. Basically, their hands are attracted to the wire now, and they're stuck to it. All right. So it's unfortunately, it's an unfortunate situation. But we have this idea that there is a force involved with electricity. We call this electric force. All right. Again, this electric force is created by an electric charge. So first off, we actually have a formula for charge. All right. The symbol for charge will be Q, and the unit for charge will be the coulomb, C, capital C. And so again, without this charge, we're going to see in a formula in a minute, you won't have a force. You need to have charged objects, two charged objects. All right. And so that leads us to my formula. Force for electric charge, it is force equals K times QA times QB over R squared. So in this formula, it's weird. There's two different charge formulas. In this formula, we always do lowercase q. In a different one, you're going to see it's uppercase q. You can use uppercase q here. It doesn't matter again. All right. But we have two different charges, charge A and charge B, being multiplied by K. What the heck is K? It is called Coulomb's constant. That'll be given to you on all your tests. 9 times 10 to the 9th. Newton meter squares over Coulomb squared. Again, that's just a constant. The units are developed based on what you're trying to calculate. The thing is, you should notice here, the force is directly related to the charges, because they're on top. Force is directly related to charge. Okay, so you can see a relationship here. If I double the charge, I'll double the force. Okay, but force is inversely related to the square of R. What is R? R, again, is the distance between those two objects. Okay, so again, it turns out the distance is going to be more important than the charge themselves. All right, you'll have an exponential change in force based on distance. You have a linear change based on charge. Right? Now, again, you can play around with this and go, well, what if I double both charges? Well, that means it's going to be 4 times the force, because you're doubling both. Okay? Force is related to each charge directly. If there's two charges, basically multiply those two factors together. All right? But it's related to 1 over R squared. So basically, my question is, have we seen a formula? Have we seen a formula like this before? Okay? Have we seen a formula that's force equals some constant times something other than charge over R squared? And we have. All right? It's related. It looks similar to the gravitational force formula. All right, gravitational force is, again, the gravitational constant times the masses. So there are gravitational forces acting between these charges as well, regardless if it is charged or not, because they do have mass. And again, it's related to 1 over r squared. So there might be questions going, how are the force formulas related? How's gravitational force related to electric force? All right. Well, we could say they're exactly the same because both of them are related to 1 over r squared. They both have the r squared formula at the bottom. But again, there is, besides obviously mass versus charge, there's another big difference. And that is, gravitational force is always an attractive force between the two objects. Always, always, always. It's an attractive force. Electric force can be repulsive or attractive because we can have opposite charges. When I have the force formula, right, this is Fg, Fe, K, Q over r squared. All right, Q over r squared. Q's can be oppositely charged. All right, basically when we say we have a negative force, all right, which in AP physics we actually make this into the absolute value on this side because basically we're not interested whether it's positive or negative so much. Okay, and on the other side, I should put that on both sides. But for regular physics, be aware you might be getting ones where it comes out to a negative force. That just means the objects are actually attracted to each other. So negative force means attractive, okay, while a positive force in these problems will be repulsive. Okay, is what we're looking at there. All right. So I think we have one more problem. We're done here. So let's say I have an example. I have a sphere. It has a charge of 6 times 10 to the negative 6 coulombs, and sphere B has a charge of 3 times 10 to the negative 6 coulombs. If they are 3 centimeters apart, what is the force between the two spheres? Is the force attractive or repulsive? Well, oh, see, this is poorly written. Negative 3 times 10 to the negative 6 coulombs. Okay. So we can answer this second question immediately. I have a positive charge and I have a negative charge. What does that mean? It should be attractive. Okay, this is going to be an attractive force between the two objects. All right, but let's go ahead and solve. All right. Let me again make sure here. Okay. So let's go ahead and solve this. We had one charge that was 6 times 10 to the, oops, see, I'm going to have to keep going back and forth here. 6 times 10 to the 6, oh, darn. 6 times 10 to the negative 6. Be prepared for scientific notation on these. 6 times 10 to the negative 6 coulombs. That's one charge. I'll just call it Q1. Q2 is negative 3 times 10 to the negative 6 coulombs. K is 9 times 10 to the 9th newtons, oh boy, yeah, Newton meters squared over Coulomb squared, sorry. All right. And the distance between the two, I think, was 3 centimeters. Yep, 3 centimeters. Okay, which that immediately has to be changed to meters. These formulas are in the base unit, 3.03 meters. All right, and so it says calculate the force. So I just plug it all in. Fe equals 9 times 10 to the 9th times 6 times 10 to the negative 6 times 3 times 10 to the negative 6 divided by 0.03 squared. I need my calculator. I'm going to calculate it. We actually have a force of 180 newtons between the two objects. Sorry, technically this would be negative 180. In AP physics, it would just be 180. Okay, we would only be interested in the magnitude of the force. Okay, So 180 newtons of force involved in this between these two spheres. All right. One last thing I just thought of in terms of another relationship between gravitational force and electric force. There are often questions of which one is stronger. The answer there is gravitational force is is generally considered to be less than the electric force. And one reason we can say this is because of the constant, all right, in that formula. The constant for gravitational force, I believe, was what, 6.67 times 10 to the negative 11th? Well, the constant for this one is 9 times 10 to the 9th. So, electric force is generally much larger than gravitational force between two objects. Okay? The gravitational force is many more magnitudes larger than the gravitational force between those charges, because those charges would have gravitational force between them, but electric force is much, much larger. All right. I think that's it. Thank you.